Welcome, everybody. It's my absolute pleasure to welcome you to the 8th annual Toronto Machine Learning Summit. My name is Faraz. I love pizza, and I'm in Toronto. And where is everyone else from? If you can let me know in the chat, I would love to know where you're from. Before we begin, I would like to acknowledge that I stand on the traditional territories of many nations, including the Mississaugas of the Credit, the Anishinaabe, the Chippewa, and the Wendat people. And it's now home to many diverse First Nations, including the Métis and the Inuit people. I also want to thank all of our incredible speakers for sharing their knowledge, all of our sponsors, including RBC, who is also our platinum sponsor, and my team, Dave, Tina, Val, Jen, Amy, the volunteers, and obviously you. Thank you so much for being part of the community. A couple of housekeeping items. All of the sessions are being recorded, and we'll be able to share all of the sessions after the summit. If you have any questions, feel free to ask them in the chat, and we'll go through them as we go through, also in the end as well. So it's my absolute pleasure to introduce our first speaker, Zain Hassan, for his talk on scaling vector databases. Zain is a senior developer advocate at Weaviate, which is an open source vector database. He is an engineer and a data scientist by training, who did his undergrad and grad work at the University of Toronto, building AI-assistive technologies. He also founded his own company, developing a digital health platform that leverages machine learning to remotely monitor chronically ill patients. So welcome, Zain, and over to you.
Thank you so much. Can you hear me all right?
Yes, I can hear you.
Okay, great. It's so great to be here. So originally I would be there in person, but I was traveling for a conference, so I had to deliver this talk virtually. But nevertheless, I'm really looking forward to this talk, and I know everybody says that they're looking forward to the talk, but this is the first time that I'm delivering this talk, and this topic is quite near and dear to my heart. I've been learning about this over the last year, and it's pretty magical. So what I want to focus on in this particular talk is I'll introduce what vector search is, what a vector database is. It's not that complicated, but really what I want to focus on is how you scale vector search and how you put it into production while still maintaining your budget. Right? And so we'll talk about vector quantization and then adaptive retrieval as well. Okay. So I work at Weaviate. Weaviate is an open source vector database. More importantly, I'm very passionate about AI. I've been in the field for a while, and I believe in the good that it can do for humanity. I'm also very passionate about open source software. So just a little bit more details about it. As was previously mentioned, I'm an engineer. I studied at the University of Toronto, and then in grad school, I got into data science and machine learning, and I've been in the field ever since. I'm very passionate about AI. I like public speaking. Started off in grad school teaching, and then I've been doing it ever since. And then over the last 2 years, I've been working a lot with open source software and community development. So this is another passion of mine. A little bit about Weaviate. Weaviate is a fully remote company. It started off in Europe, but a lot of the work that we're doing now is in North America. It was one of the first vector databases, and it's very popularly used now. So I'll talk a little bit about what vector databases are to start off the session so that everybody's on the same page. And then I'll also be kind of going back and forth to look at the chat here on the other screen. So currently I've only got one screen, so I'll have to do a little bit of juggling. Okay, so the idea behind vector databases is imagine you've got all of the files on your computer here. So this can be emails, these can be text documents, PDFs, images, audio, video files. You're going to take all of this data, and just for simplicity, imagine for now this is only text. Later we'll talk about this being other types of data, but for simplicity's sakes, we can just take that to be text right now. We're going to pass that through some machine learning model. And the point of this machine learning model is to generate vectors of this data. And so a vector is just an array of floating point numbers, and every object that you had here will generate one vector, right? So it's a one-to-one mapping of one object to one vector. And the cool thing about this conversion from human understandable data to machine understandable data, you've got your human understandable version here and the machine understandable version here, is that this machine learning model has been trained such that it, in this translation from human to machine version of the data, it preserves a lot of the meaning behind the data. And the way we can see that it preserves meaning is that if you plot out these vectors, as I've done here, one green dot equals one vector. And usually these vectors are very high dimensional, anywhere from 1,000 to 4,000 typically. So one vector would be 4,000 numbers or 2,000 numbers, depending on which model you use. But here I've kind of shown a three-dimensional version of it. The cool thing about this translation into vector space is that the semantics of the data is retained. So if you've got objects that are similar in concept, i.e. the word chicken and the image chicken, the vectors are going to be in close proximity to each other. Whereas if you have concepts that are dissimilar, like the word chicken and image of a banana or the word banana, now those two things are going to be far apart in vector space, right? And so the critical component here is that whatever machine learning model you use, because it's been trained on data, it is able to preserve the semantics of your data such that it knows the difference between similar and dissimilar concepts, and it kind of pushes away dissimilar objects and it pulls together closer similar objects. Right? And so this is kind of the fundamentals of how a vector database works. Another way to think about this is if you think back to how classification in a library works. If you walk into a library, the locations of the books are going to be dependent on what the books are about, right? So a book on chemistry is going to be in a very different location compared to a book on pottery or arts and craft. And so the way I kind of think about vector databases is through the analogy of a library. Every data object that you have, depending on the machine learning model, gets a space in the library, and that space, it'll have similar books that are related to that data object in and around that proximity. And the point of the vector search engine or the vector database is to act almost like a superhuman librarian, where the user comes in, says, these are the queries that I'm interested in, these are the topics that I'm interested in. Maybe I want to learn about cheetahs, so give me books about cheetahs. The vector database, the librarian then goes out and picks out the books that are semantically relevant to your query, and it brings them back, and then you can do whatever you'd like with them. Right? And so this is the high-level idea of how a vector database works. So when you're performing vector search, the first step you have to do is take all of your data and you have to index it. You have to turn it into vectors, and then you have to kind of generate all of these green dots. The next thing that comes in is the user with the query. So we can visualize the user with the query as this red dot over here. And the really great thing about vector databases is that the query is actually just kind of a natural language sentence. It doesn't have to be a SQL query or anything like that. It's actually just a natural language sentence, and it goes through the exact same machine learning model to generate the corresponding vector. And the act of vector searching is effectively saying which of the indexed green objects in my database are semantically related, which of them are the closest in meaning to the query object, and those are the ones that I'm going to return to my user. Right? And so in a nutshell, the vector search pipeline looks something like this. Right? You start off with a machine learning model that can capture and translate the meaning of your data from human to machine version. You pass in your data through this pipeline of the machine learning model. You take the vectors that come out on the other side and you populate them into a vector database like Weaviate. The user comes along with their query. It goes through the exact same pathway, typically, goes through the machine learning model. You get a vector out for that query that goes to your vector database, and then you perform some form of nearest neighbor search to see which objects are in the nearest neighborhood of my query. And then you take those and you retrieve those and send those back to the user. And so this is what the vector search pipeline typically consists of. And so specifically, this talk is about kind of detailing and laser focusing in on the vectors themselves. So one of the most expensive things about vector search is storing the vectors and then performing nearest neighbor search over the vectors. So I wanted to detail and look at what are these vectors. So how big are they? What are they? How much space are they taking? So typically, let's say you have V1, vector 1, and then you've got an let's say an n-dimensional vector for now. Let's say it's 1,000 numbers, and I've just shown some of them here. So typically, each number here, so this each number will be a 32-bit floating point number. And so you can now think of this as every number that you've got here, that's a floating point 32-bit, and then another one, and then you've got however long the dimensionality of the vector is, you've got that many floating point 32-bit numbers. And so if you do a little bit of back of the napkin calculation, one vector is about 1,000 numbers, and each number is about 32 bits. So that's about 32,000 bits per vector. Right? And so that's about 4 kilobytes. And so if you have a application where you've got millions and millions of vectors, this scales up really quickly. And so the main cost of running a vector database in production is all these vectors need to be stored in memory, in RAM. And so when you're performing vector search, if you have millions or billions of objects, it's going to cost a lot to maintain that memory. And so the whole point of this talk is, what can we do when we're at the million or even billion level vector search scale, so that costs are still under budget, and then maybe we have a way to um, balance costs versus accuracy. We might not want the fastest or the most accurate application, but we want something that's under budget. Okay, so I'll talk about some solutions that help us address this. Okay, so a little bit of the motivation behind why you should be interested in vector quantization and adaptive retrieval. Why even care about this talk? Okay. So the motivation here is very simple, actually. This is the simplest part of the talk. It's about money. Okay. So let me do a quick demo here. So here, if you just think about how much it's going to cost you to do in production vector search, there's a quick kind of pricing calculator here. Let's say you've got vectors that are about, let's say, 1.5K dimensions, right? So every object is going to get turned into 1,500 numbers, and then every vector is 1,500 dimensional. So that's approximately, we'll put that in here. Let's say you've got 10 million objects. So you've got this much, and then so the cost of running the vector database is about $1,500 a month. Right? And so this is just keeping everything standard. And then there's one option here, so that's storage type. If we go down here and we say, okay, compression, so this is without compression. It's about $1,500 a month. If you enable compression, look at what happens to the price. So this is almost a 90% reduction in price when you enable vector compression, as opposed to if you don't enable vector compression, right? And the thing here is that typically, because of all the work that's happening in the field, this number is trending upwards. So a lot of the newer models, you might even get models that are 4,000 dimensional. And so that increases prices a lot. And so let me decrease that a little bit. That increases prices a lot. And then as you get more and more objects in your pipeline, this is also going to increase the costs here. Right? So you can get to a point where it's pretty much unfeasible uh, based on how much it's costing without compression. Right? So compression is a very big deal. And so I was teaching a course about a couple of weeks ago in Seattle, kind of showed them this, and this was a kind of a light bulb moment for them. So I thought I'd give you this demo as well to talk about why you should care about vector quantization. Right? So a lot of what I'll talk about in this presentation is how do you get that 90% reduction in costs while still maintaining a lot of the accuracy that you've got. Okay, awesome. So let's keep going. So yeah, question, go ahead. I'm not, I don't hear anything. So I'll continue, and then maybe if I see the question, I'll stop and answer it. Okay, so at this point, so like I said, it's the easiest part of the talk. It's when you can reduce price by 90%, there's not much more convincing I have to do, right? So that's enough said on motivation. So let me quickly get on to the technical component of it. Like, what is compression? What is quantization? how do I sign up for it, right? So compression is actually quite simple. It's not very difficult to understand what's going on. Imagine you've gotten this image, and what you want to do is compress it. You'd like to store it, and you want it to take up less memory. One way to do that is simply kind of reduce the number of possibilities that you can have in the color palette, right? You've got the exact same number of pixels between the two images, but the amount of the different values that the pixels can take up is kind of thresholded and limited here, right? This is why you don't get like smooth transitions in color. You get these big movements in color, and you can actually see them. So this is more of a quantized compressed image where the pixel values are now quantized to be very specific values. And so if you look into this a little bit more, what you're effectively doing is you're limiting the color palette of the painter that painted this image, right? You're saying you can no longer use any shade of color you want. You have to use only these 16 shades, right? And so what the painter now has to do is decide, if I'm going to go from this image to this image, how do I take these different shades of blue in the background, these different shades of white and black and so on and so forth, and then how do I project them in such a way that I can maintain as much of the image as possible? Right? And so what you're doing here is you're quantizing and compressing the image. And this is very close to what we're doing with vector quantization, actually. So it's quite intuitive. You want to save as much space as possible while sacrificing as little of the meaning behind the data object as possible. And so the question is, if our vector embeddings need to be in memory, and this is a pretty important question. So um, we're working on a feature now where they don't technically need to be in memory, but a lot of the main kind of in-prod solutions for vector search, the vector embeddings need to be in memory, right? So we'll take that first part of the question as a given for now, and then we want to ask, if we do have to keep all the vectors in memory, can we reduce their footprint? Instead of storing the full vector, can we maybe reduce the size? And if we can, then there's a lot of cost savings to be had, as I just showed you in the quick kind of pricing calculator demo there. Okay, so typically, if you're working with vector databases or if you're doing vector search, you're using one of these models from OpenAI or Cohere or one of the open source models here. And like I said, the dimensionality of the vectors is not getting smaller; it's only trending upwards. So the really popular Ada 2 model is 1.5K dimensions. Cohere's new models are at a maximum about 4,000 dimensions. And so if you look at the number of the size of each vector, it can range from anywhere from 6 kilobytes to 16 kilobytes, or 3 kilobytes if you're on the lower end here. And so for 1 million vectors, this requires 6 gigabytes of RAM. This is not accounting for any of the other overhead, just pure vectors. So this is at least the least minimum. You would be a lot higher than this because you have to account for all sorts of other things. And if you've got 1 million vector search application, 1 million is not even that high, right? So you need 16 gigabytes of RAM, assuming that you've got a 4K dimensional vector. Okay, let me just see if there's any questions. Faraz, I'm not seeing the question, so if possible, if you can type them into the chat, if there's any really pressing questions, I'd appreciate that.
Yeah, absolutely. 1 second.
Yeah, awesome. Okay, cool. So the number of dimensionalities is trending upwards. A lot of people were building POCs with vector search, and now they want to go into prod. So data has to scale up. The number of objects scales up. So both of these numbers are trending upwards. And so we need a way to scale and then still remain within budget. So the whole point of vector compression and quantization is we want to take our vectors, whether we have millions or billions of them, and each one here is a floating point 32. We want to compress it and quantize it, right? And there's multiple ways that we can do this. I'm going to propose 4 different techniques to do this. And so we can compress them. Maybe we take a int8 representation where every dimension is now a 8-bit integer instead of a 32-bit floating point number. And now we save a lot of space doing this, but we're paying a price for this, right? And so we want to make decisions so that um, we can take that balance of saving space and then also not losing too much accuracy. And so because all of our objects now, each object gets turned into a vector, we'd like to compress that vector, and there's a lot of savings in that, right? So now I'm just going to go off one by one into different quantization techniques and show you some of the experiments that we've ran in terms of how much money is it going to save you versus how much of the accuracy are you going to have to give up if you want to use that quantization technique. So first on the docket is a technique called scalar quantization. And the idea behind scalar quantization is actually quite simple. Imagine you've got some form of signal that looks like this. And here in this image, I've shown a continuous valued signal, right? So for every x value here, you've got a continuous valued y coordinate. And then you can see it's a very smooth kind of curve. The whole point of scalar quantization is every y value here, instead of making it a 32-bit floating point number, you're going to squish it into a 8-bit integer. And so if you do that, the signal will now look like this, where you've got like these quantized jumps. And so now it won't be as smooth. So you've got these kind of, this is why it's called quantization, because you're taking these kind of small thresholded jumps now, but you're saving a lot on memory. And so this is very similar to the example that I showed with the image, except now instead of having a 16 kind of color variation optionality with 8-bit quantization, with scalar quantization, you've got 256 colors to choose from. And so it won't be as obvious as this in terms of the ocean having this kind of very large shifts. So it won't be that bad. But if you look into how many pixel values there are, you'll actually see that there's only 256 options here. So one application of this is, imagine you've got this vector. When you so this is floating point 32-bit. If you quantize it using scalar quantization, it'll turn into numbers that now look like this, right? So it'll have to be a number between 0 and 256, and this is what that will amount to. Yeah, so let me just look here. Yeah, so Brian asks, what kind of semantic info can be lost during quantization? This is a good point. So it's not clear because the embedding model that you're generating is not doing the quantization. You take the embedding from that embedding model and then you do quantization afterwards, right? So there is some work now where companies are actually quantizing the loss function takes into account quantization, but on a high level, what quantization does is it makes the vectors a little bit fuzzy. So if you have a 32-bit precision vector, you know exactly where that vector is down to kind of a certain accuracy. But now if you quantize it, there's a region where that vector can be, and you don't know where in that region that vector is. So this is the kind of semantic information that you lose. Maybe you're now no longer able to differentiate concepts that were previously distinguishable. Um, Previously, you might have been able to tell the difference between different species of animals, but after quantization, you might no longer be able to do that because the kind of the model's representation for those different species is actually quite close, and it requires the full precision of the floating point number to take that into account and to distinguish between those two species. But now when you've cut that off, now maybe all those species get turned into one vector and you can't distinguish between them, right? So that's how you want to think about losing the fine-grained information that these models can encode. Is it possible to introduce, another question is it possible to introduce different kinds of quantization, both 4-bit and 8-bit into a vector, into a single vector DB? Yeah, it is, and this is what I'll get to when I talk about adaptive retrieval. Another question is the needed dimensionality of the embedding model driven by the scale and variability of the documents you're storing? Not necessarily. So the dimensionality of the embedding model is purely driven by the embedding model trainers. So uh, for And you can think of it as if you have more embedding dimensions, then you can store more information in those dimensions. Um, and so when we talk, embedding models are separate, but when you talk about language models, you often see that if you have a 70 billion parameter model, and you can compare a 70 billion parameter model now to a 70 billion parameter model that was released a year and a half ago, even though they might have the exact same number of parameters, this model is using those parameters a lot better than the previous parameters. Right? So just because an embedding is twice as large as another embedding doesn't mean that it's going to be much better. It depends on kind of the information that's distilled in that in the weights of that model. And then typically you don't pick an embedding model because of the dimensionality. You typically pick it for its performance on your particular domain that you're interested in. Right? So you can start off with standard benchmarks and see which models perform better. And then you can see, okay, if I have a medical application, which model performs better in the medical or the biomedical domain? And then to improve that further, you can fine tune the model above this as well. And then there's a question, how do you determine the optimal balance between memory usage and cost and quantization loss? So this is a good question. I'm actually going to get to this in a future slide. And then some of the other questions that I've skimmed over, I'll get to at the end of the presentation as well. Okay, so the whole point here was if you're now turning a 32-bit, so if you're going through this motion of taking a 32-bit number and then you're quantizing it, so now you've got only 256 levels to choose from, you're going to lose out on accuracy, right? So the question is how much? So we ran experiments where because you're going from 32 bits now to 8 bits, you're saving 75% on memory. And then we ran experiments with the OpenAI encoded DBpedia dataset where we've got 100,000 vectors, and where these results are on a test set of 500 query vectors. And so the loss in recall is about 5%, which is not bad. So if you think about it, it cuts your bill in 1/4, and you only pay 5% recall for this. Um, but it's still, you kind of have to balance this. So this is a pretty good result, and I'll talk about kind of measuring how well the other techniques measure up to this technique now. Okay, so the advantage, of course, of scalar quantization is that it's a 4x reduction in the storage space. Um, Another optimization here is that because now you've got vectors that are int 8s instead of floating point 32 bits, the math between calculating the distance between these vectors, because that's another kind of problem that vector databases have to deal with, you have to do lots and lots of vector distance calculations, and each vector distance calculation costs time and money. The int vector distance calculations are a lot faster and easier to do, and you can do hardware optimizations around them, whereas float vector distance calculations cost more. The recall is decent, right? So you're cutting your bill by 1/4, and you're only losing 5% recall, which we can also get back using adaptive retrieval, which I'll talk about at the end of this session. And then the other advantage here is that you can tackle data drift very easily, because when you fit a scalar quantization solution, the only thing that you have to worry about is what is the range of your vectors? What is the minimum value that a vector dimension takes up? And what is the minimum or the maximum value that a vector dimension takes up? And so if you've got data that's shifted, you can take the min-max calculation, really simple, and then you can refit your scalar quantization again really quickly. So it's a very cheap solution, even if you have data drift over time. The problems with scalar quantization is that if you've got outliers in your data, because you're taking a min-max, so if you think about vector normalization, if you do a min-max normalization, if you've got anomalies where your maximum is 1,000 times larger than any other maximum for any other vector, it's going to squish everything else, right? So this is not very robust to outliers, or if your minimum is very small compared to the overall minimum, or the average minimum value, then it can squish your data in the wrong direction. The other problem is that this advantage is actually a disadvantage here. Right? you can tackle data drift because you're not that dependent on the data. You're only looking at the maximum and the minimum value of the data. But this also means that you're not that dependent on the data. And ideally, we'd like quantization techniques to respect and use the underlying data distribution as much as possible. And then the other problem here is that if you do choose to go to, there's a question about 4-bit quantization. If you do choose to more aggressively quantize, so you do 2-bit or 4-bit quantization, the recall massively drops off. You go from 95% at 8-bit quantization to, if you do an 8x reduction, you're now at about a 29% recall. So it's a massive loss in recall. Okay. And this is something that we've implemented, and it's coming out in probably the next 2 weeks with Weaviate. So if you're using this, you can simply configure it and you can turn it on and you can take advantage of it. The second quantization technique that I'll talk about is called product quantization. And product quantization is probably the second most interesting technique. It's pretty cool. So the idea behind product quantization is, imagine every vector is a black dot here. And so ignore the white stuff for now. Every vector is, I'm showing it as a 2-dimensional object here. This is a black dot. What we're going to do is we're going to cluster this using any clustering algorithm. So you can think about it as k-means clustering algorithm or hierarchical clustering, dbScan, whatever you'd like. Typically, for this application, we actually just use k-means clustering. But we created this kind of Voronoi diagram where now you've got these regions in vector space where you've got a cluster centroid that's going to capture any vector that lands inside this region. And so now if you think about it, any vector for any object that belongs to this region gets mapped to this vector centroid, this cluster centroid. And now we throw away the vectors. We don't actually throw them away. We store them in disk. We don't keep them in memory, so it's a lot cheaper. So we put all of the actual black dots on disk because they take up a lot of space and disk is cheaper. And in memory, we only keep the cluster centroids here, right, from k-means. And so this is what product quantization is doing. The problem with this is that now, previously, you could tell the difference between this vector and that vector, right? You can calculate the Euclidean distance between those two vectors. But after you quantize, you can no longer tell the difference because both of those vectors are now mapped to this cluster center. And if you say, what is the distance between this vector and that vector, which used to be here, well, now it's 0 because they're right on top of each other. They're assigned the cluster centroid. And so this is the type of meaning that is lost. And there's a question about what information gets lost. If the vectors were close enough before quantization, after quantization, they're going to be exactly the same. Okay, so typically here, you can set how aggressively you want to quantize, but let's say you want to do a unsigned 8-bit integer quantization where you take every dimension and now you kind of project that into 256 clusters. Right? So this depends on your data, but these are the kind of the default settings that we provide, and then you can configure them and change them later on. But typically the idea is that you're going to apply this per dimension level, and you have to choose how many clusters to fit k-means with. And so 256 is a good option. And to store 256 cluster centers, their IDs, that's a 8-bit integer that you require to do that. And so typically, if you do this for one vector, so you have the 0th position, you have the value, and the value is then going to be assigned a cluster ID. And this cluster ID, you have some sort of dictionary or lookup, which actually tells you the location or the dimensionality or the value for this cluster. But what you store in memory is just the ID for that cluster. And then you have some sort of code book that goes from cluster IDs to actual cluster locations in vector space. And so here, it's very good because you can choose how much to quantize, right? You can choose to assign 256 clusters per dimension, as is shown here, or you can say, I'm going to take this vector, so now it's a 2D vector, and I'm going to learn 2-dimensional cluster centroid, so now it'll be a 2D vector, and then I assign this ID to a 2D cluster centroid. So now you can adaptively choose how much I want to quantize, how little I want to quantize, and then you can plot that out versus how much loss and recall you have to pay for the quantization. And so this is also now a hyperparameter of how much do you want to squish your data. And the more dimensions you turn into a segment, the more you're going to squish your data, because you have to store less cluster IDs in memory. You're just having a look at one of the questions. One question says, is it feasible to implement dynamic compression in vector databases, applying it only when it won't critically impact data quality to optimize cost and memory usage? Yeah, so this is a great question. I'm actually going to get to this when I talk about adaptive retrieval, because adaptive retrieval addresses exactly this problem. There is also a separate feature called automatic quantization that we have in Weaviate, where it'll look at how much data you have, and then when you reach a critical threshold of data, we will turn on quantization for you, and before that, it'll automatically have quantization off, right? So we kind of manage that for you as well. There's a question: is there a trade-off between quantizing the data 32-bit to 16-bit rather than trying to reduce the dimensions? This is also a great question. I'm going to defer that because I have one of my quantization techniques is actually talking about just cutting the vector in half, and it's I'll talk about that when I get to those slides. So a lot of these questions are kind of predicting what I'm going to talk about, so this is great. Awesome. So let's keep going here. So if you think about how does product quantization fare up against scalar quantization, again, these are experiments on the same data set, 100,000 data set. The test set is 500 query vectors. And here, where the hyperparameters that we've set is that we take chunks of 4 dimensions, so the first 4 dimensions, the next 4 dimensions, the next 4 dimensions, and we turn them, we cluster those together, so we get a 16x reduction in memory. So if you compare it to scalar quantization was a 4x reduction. This is now a 16x reduction, and the loss and recall is now about 17%. So 5% for scalar quantization, 17% for product quantization. So there's a sad face there because now you're losing on recall, and of course this is a balance. The good thing about product quantization is that the compression rate is dynamic. You can choose to compress very aggressively, or you can choose to compress very slightly. And now it's a kind of almost a sliding window of how much you want to compress depending on your application. So if you do want to, a question was asking about balancing between recall and memory savings. Product quantization is a very good, robust way to do this, because if you compress too aggressively and you find all of a sudden that the search is giving you irrelevant results, you can quantize less. Right? PQ has a hyperparameter that allows you to increase or decrease that on the go. You can actually improve this with adaptive retrieval, as I'll talk about in a second. And this is the default quantization technique that is enabled in Weaviate, because you can modify it as you go. The problem here with PQ is that imagine you fit a k-means clustering to your data set, and then you import 10x more data. You're going to have to refit the k-means clustering algorithm, recalculate the cluster centroids, and if the data distribution shifts, then that's fairly expensive, and you kind of have to, you can't just do it on the go. So requantizing your data underneath data drift, and if the data distribution changes, is pretty expensive here. And also the vector distance calculations here between PQ quantized vectors is probably the slowest out of all of the 4 quantization techniques that I'll talk about. Okay. And product quantization, like I mentioned, is generally available in Weaviate. So you can, if you spin up and use Weaviate right now, open source or the managed version, it's you can configure it and you can enable it. You can look at the kind of the memory savings that you get with it versus without it. Okay. So now we'll talk about binary quantization. Binary quantization is a very radical idea. The idea behind binary quantization is, we've got 32-bit floating point numbers for each dimension. How much information can we throw away? So you go from kind of going from 32-bit to 8-bit, 32-bit to a dynamic kind of compressing with PQ. BQ is all the way on the other scale. BQ says we're literally going to binarize each dimension. We're going to go from 32 bits now to just 1 bit. And so just to give you an idea of what that looks like, if we go back to our image analogy, imagine you've got this image here on the left-hand side. If you binarize this image, this is what it would look like. Right? So this is a binary, just black and white image. And literally all I'm doing here is saying if the pixel value is greater than a certain number, turn it to white. If it's lower than that certain number, turn it to black. Right? And so now you can see you lose a lot of meaning when you binarize an image. Right? And so as you can probably expect, if you binarize a vector, you're going to pay a heavy price. But the advantage of binary quantization is that this requires a lot less memory compared to this. And as you can see, the details are a lot less. So if you look at what that does to a vector, this is just kind of a pictorial representation of what a vector would look like. It kind of looks like a barcode. So here you've got a 300 something dimensional, 380, 90 dimensional vector. And if you binarize it, you're effectively saying, is the number at that value greater than or lower than a certain threshold? And then you kind of just turn it into black or white. And so this is what your binary quantized vector now looks like. If you guys are interested, there's a whole blog that I wrote on this that goes into just kind of exploring binary quantization all the way up to benchmarking and looking at what that process looks like that you can go into for details. But this is pretty radical, right? You take your 32-bit vector and you turn it into a 1-bit vector for every dimension. And so if you so typically how this is implemented for vectors is you just look at the sign. If the sign is positive, you turn that into a 1. If the sign is negative, you turn that into a 0. So this vector, this 4-dimensional vector, would turn into 1, 0, 0, 1 because you have positive, negative, negative, positive, right? So 1, 0, 0, 1. So this is a very aggressive compression technique. And a lot of people would think, well, how does this even work, right? How can you tell the difference between this and it actually works really well in practice. And the reason why is because the vectors are very high dimensional. And so the number of unique vectors that you can have grows exponentially as the dimension of the vector grows. So if your vectors are only 4-dimensional, this technique would be horrible. But thankfully, the vectors are very high dimensional. They're anywhere from 1,000 to 4,000 dimensional. So the number of unique vectors that you can have is growing exponentially per dimension that you add. And so binary quantization is actually quite powerful. So if we talk about numbers, how powerful is it? On the same data set, you get a 32x reduction. So you go from literally 32 bits per dimension to 1 bit per dimension, 0 to 1. And the loss and recall here is pretty noticeable. Right? Like I mentioned, if you look at a non-binarized image and a binarized image, it's clear that you've lost a lot of information. So you lose about what is this 35% recall. And so this is pretty horrible, but this is not the end of the story, right? We're going to come back to how can we improve on this, but this is just purely quantization, no adaptive retrieval for now. Right? So this is by far the worst result that we've gotten, but we should have expected this because this is such an aggressive kind of quantization technique here. Yeah, let me go to the questions for a second. So there's one question that says 95% recall rate in this case means 95% able to retrieve answer back, or the information retrieved is 5% less. 95% recall rate here means that for everything that you were expecting to be returned, you've only got 95% of the objects, and 5% of the objects are actually irrelevant. So of the positive things that you wanted to retrieve, it's only giving you 95% of them. The other 5% are irrelevant. Right? So you're actually looking at how much of the positives that you wanted, the good stuff that you wanted to be returned, how much of it is actually being returned. Okay, just quick time check here. Okay, we've got more than enough time. So the advantage of BQ here is that it's the most compression that we've talked about so far. Another advantage is that because we now have binary vectors, only ones and zeros, you can really take advantage of hardware optimizations to calculate distances between vectors. Now you're calculating the Hamming distance between the vectors, and literally all you have to do is, if you're calculating the distance between two vectors, you just have to check if the dimensions, if the numbers in the dimensions agree or don't agree. And so that's called the Hamming distance, and you can take advantage of hardware optimizations to do this really, really quickly. And so we put out a technical blog post on this, on how we used Intel's new Sapphire Rapids to do SIMD optimized Hamming distance calculations to speed up Weaviate uh, a lot, right? So you can look into that, and it's pretty exciting. The other advantage here is that there's no fitting required for BQ. All you're doing is dropping all the information, only keeping the sign of the dimension, and so it's completely independent of data drift. The other advantage here is that if you fine tune or train a model to respect the fact that eventually you're going to be using only the sign of the embedding of the dimension of the vector, you can actually squeeze a lot more recall out of this. So Cohere is a Toronto-based company that's training these embedding models, trained an embedding model that was kind of aware of quantization. So it's a quantization aware model. The loss function takes into account the fact that the embedding is meant to be quantized later on. And they got very high recall. If I remember correctly, it's 90 to 95% recall with binary quantization. So these results that I'm showing here are for models that are not quantization aware. So this model did not know that you were intending to use the sign of the embedding. It thought you were going to use the full 32 bits. So if you train the model with quantization aware loss functions, you can actually crank up that recall a lot more. And in fact, for a lot of the really small use cases, we enable BQ by default because it's really quick. And then you can even use brute force search. You don't have to do approximate nearest neighbors. And this is how we serve a lot of customers that have lots and lots of vector indices. Where let's say you've got you've got a million customers and you want to do vector search over only one customer's data at a time. So there you have to have a million kind of vector database instances, and each one might not have a lot of objects, right? So for that solution, we just default to binary quantization. Problems, of course, very low recall. I'll talk about how adaptive retrieval addresses this and solves this in a second. The other problem here is that you're assuming that the vectors are normalized. Right? The vectors are centered around zero so that you can take the positive and the negative. You can only look at the sign. If I give you a vector that's always positive, then the binary quantization of that vector is going to give you no information at all. Right? If I give you a embedding model that only outputs positive vectors, then the BQ quantization of that embedding, the vectors coming out of that embedding model, is going to give you no information at all. Right? So it requires that your distribution is normalized around zero. And binary quantization is generally available, and you can, if you start using Weaviate, if you're using Weaviate, you can just configure it and you can enable it. Okay. And the last technique that I'll talk about is called Matryoshka vector quantization. So this goes back to the question that I was mentioning earlier. So one of the questions said, instead of taking every dimension, and so every dimension is 32-bit, and then if we want, we can squeeze it into 8-bit integers or 1-bit binary quantization. Instead of doing that, why don't I just use the first 500 dimensions or the first 100 dimensions? And so this is exactly what Matryoshka representation learning and Matryoshka vector quantization does. So the idea here is I use a very small subset of the dimensions, and it's literally as easy as dropping the next X dimensions, right? So there's an interesting experiment that I ran where I took a large data set and I sampled 10,000 vectors, and then I looked at the standard deviation per dimension of the vector. Right? So this was an eta 2 model, so it's 1,500 dimensions. On the x-axis here, you've got the dimension. So this is the first dimension, the 200th dimension, the 40th dimension, and then what I did is I took 10,000 vectors and then I averaged, I looked at the standard deviation on that dimension index for all of those vectors. And so if you've got non-Matryoshka vectors, and I'll explain what that is in a second, but if you've got classical vectors, you'll see that there's a pretty constant standard deviation per dimension, right? It goes up and down a little bit, but it kind of averages out. And you can think of the standard deviation per dimension as the importance and how much information is captured by that dimension, right? And what this tells you is that every dimension is equally important to any other dimension, right? There's no one dimension that is all important and another dimension that is completely useless. They all capture variability in the data equally. Okay? So you can, if you had to choose one dimension over the other, it's very hard to do, right? If you look at Matryoshka vectors, where the idea is we want to store more information in the earlier dimensions, and as the dimensionality increases, we want to decrease the number of information. If you run the exact same experiment for Matryoshka vectors, this is what that looks like. So exact same data set, you take 10,000 random samples, the same random samples, but now the data is vectorized using OpenAI's new embedding 3 model, which is a Matryoshka embedding model. Now you can see that the first 512 dimensions are a lot more important than the next 512 dimensions, which are also a lot more important than the next 512 dimensions. And the last 1500 approximately dimensions are the least important compared to these ones, right? So now you almost get this step function of importance between the dimensions. And so now, if I asked you, you have a 3000 dimensional vector in front of you, you can only use 500 dimensions. Which 500 dimensions do you use? It's a very easy answer. Just give me the first 500 because those are the most important ones. Now, if I can afford to keep 1000 instead of 500, give me the next 500 as well. Okay? And you can keep on doing this. And so the idea behind this is that the earlier dimensions are kind of storing a disproportionate amount of information. So you can cut the vector off, and this will give you a lot more of the information that the vector is storing compared to the next chunk, and so on and so forth. And so if your embedding model has been trained in this Matryoshka style, where now the dimensions disproportionately store data, you can go ahead and just cut the vector anywhere you'd like, right? You can actually cut it anywhere. But OpenAI typically just says cut it at the 512 dimensions or the 1024 or the 1536. But if you look into the paper that explores Matryoshka and invents Matryoshka, they show that you can actually cut anywhere. So you can take the first 500 dimensions, the first 100. Typically, you don't want to squeeze it too much, but you can take like 700 dimensions, and that'll be okay as well. And so the idea here is now you've got this vector. Let's say this is 1000 dimensional. Instead of squishing every dimension equally, what we're going to do is literally just take this floating point 32 1000 dimensional vector, and when we use Matryoshka to quantize it, we're literally only going to use the first 500 numbers, or we're only going to use the first 100 numbers, right? And this paper at the bottom actually does an analysis of how many dimensions you want to keep, and then what the price is in terms of recall. Typically, you can keep the first 15% of a vector. So for a 1000 dimensional vector, you can keep the first 150 to 200 dimensions, and that will be more than enough. And if you take, let's say, 20 to 25% of the vector, that'll give you about 95% recall. And so here you're quantizing literally not by modifying the floating point 32, but you're just dropping off the irrelevant, or the less relevant, I should say, dimensions at the end there. And so this is a very cool technique that was only invented about a year ago. The paper came out, and now people are using it in production. The thing you have to be very about this is that the embedding model has to be Matryoshka trained. So the way they disproportionately store information is by modifying the loss function of the embedding model. And so you can't just use a non-Matryoshka vector, and you can't just chop it. Because if you do that, then what you would be doing is effectively taking this type of vector here And then you would say, okay, which dimension do I use? Which of the 500 of these 1,600 do I use? And the answer is they're all equal. You can't really pick 500 that are better than another 500. So one of the problems with this is that you kind of have to go in with an embedding model that is Matryoshka aware and trained for Matryoshka learning. Okay, let's zoom through this. So now the next part, let me just stop here and take some questions. 1 second, let's see. Does the recall rate also, so there's a question that says, does the recall rate also take into account false positives, or does it only look at expected entries that aren't returned? It only takes into account the positives, right? So it's a measure of, you can also look at precision, but typically people are interested in the positives, right? So if I have a query and I have 5 things that should be returned and only 4 of them are returned, that's a recall of 80% because that's a 4 over 5. I only get back 4 of the true positives that I wanted. Another question that says, so when it's retrieved, is it still the original text or affected by compression? That's a great question. We're not compressing the original text. We're compressing the vector representation of that text. So when you get back the original text or the image or whatever your original human understandable data object was, it's the original thing. There's no compression in that. It's only in the vector representation that's used to search for it is where we're compressing. So that's a great question. Another question is there a benefit to cutting from 3,000 dimension model to 1,000 dimensions over just using a 1,000 dimension model to start with? Yes. So typically the 3,000 dimensional vector, well, if you just specifically look at OpenAI's models, the 3,000 Matryoshka vector embedding model is a lot more powerful than their 1,000 dimensional model. So that's separate, not Matryoshka related, but it's a lot more powerful. So you just use that one. And if you use the 1,000 dimensions of this new embedding model compared to the 1,000 dimensions of the old embedding model, this is a lot more powerful because this is kind of a newer generation model. Um, if you were to compare let's say you take the same model, one has been trained using Matryoshka and one has been trained using non-Matryoshka. There, if you have a 1,000 dimensional, if you have 3,000 dimensions here and 3,000 dimensions here, if you use 1,000 dimensions of the non-Matryoshka vector, first of all, you can't just willy-nilly chop a non-Matryoshka vector. That's the special thing about a Matryoshka vector. You can chop it starting off at the beginning indices. Um, so there you have to be a little careful. If you're comparing a 1,000 dimensional vector to the first 1,000 dimensions of a Matryoshka vector, I think the Matryoshka vector will outperform. But I think it changes from domain to domain, and it also depends on the training. So I don't know if there's a general rule of thumb that can be given around that. Okay, great. So this is the last part of the talk, and this is where I'll talk about addressing all of those kind of crying and unhappy faces. Right? So the idea here is the reason why we're interested in quantization is we'd like to save on memory costs. So we want to do that 90x reduction in cost that I showed, but we'd also like to not pay the price of kind of reducing quality. Right? So the question is, why don't I just take both, right? I want to save money, but I also want really good quality. So I want to have my cake and I want to eat it too. So that is the big question, right? How is this possible? It seems like it shouldn't be allowed. It seems illegal, right? But it is possible, and let me show you how. Before I show you how, I'm gonna tell you a little bit of a side story. So this story is about a fisherman, and this fisherman is dreaming about catching this green salmon. Right? He's been kind of training for it his whole life. He wants to catch this green salmon. So what he and his friends do is they get on a boat and then they throw out this massive net. And what this massive net catches is a bunch of salmon. You know, we don't know whether the green salmon is in there or not. We just catch a bunch of fish. And then what the fishermen then do is they look through fish by fish, one at a time, and then they get the green salmon, right? And it turns out that it was caught in this big net. And so, happy fisherman, end of story. What does this have to do with adaptive retrieval? If I tell you that each fish here now is one object, and this green salmon is the object that is closest to your query, what adaptive retrieval allows you to do is perform this kind of high level search where you over retrieve, you catch a lot more objects than you want, and then you kind of narrow in on the exact object that you want, right? Similar to the fisherman here, where you over retrieve. Like a lot of these fishes are not the one that he wanted, but you look through one by one and you extract out the one that you're interested in. Right? And that is the essence behind adaptive retrieval. So if I ask you, these are all the fish, and this is my query vector, which objects here would catch the green salmon? Right? So this is quite simple. You would say how many objects are you interested in when you want to do this proximity-based search? And let's say I say 4, then the answer is quite simple. Right? These are your green salmon in this particular application. The problem is that these are uncompressed vectors, right? So you can clearly see where the vector is. There's no kind of fuzziness around it. If I ask you the same question now, I ask you find the green salmon. Now there's all sorts of artifacts and kind of shadows and kind of cutoffs and weird noisy artifacts that typically come in with compressed vectors. And this is just a pictorial representation. Um, but this goes back to what I was talking about earlier. After you quantize, you actually lose information about where the vector is, and you get this kind of neighborhood of, okay, maybe the vector is somewhere here. And so now when I ask you, find the green salmon, now it's not too easy. This is where adaptive retrieval comes in. So adaptive retrieval says, second, let me just have a look here. Okay. So adaptive retrieval says what we're going to do is instead of immediately giving you the right answer, we're going to throw out a big old net and we're going to catch anything that might be a green salmon. Right? So in our first try, notice how I said first try here, we're going to search, we're going to expand the search radius and capture anything that might remotely be a green salmon. Right? So we're going to overfetch and we get a lot more results than the user actually asked for. The user might have asked for 5 results and we give them initially 100 results in our algorithm. And then what we do is because remember, the uncompressed vectors are actually stored on disk. Right? So it's only in memory that we have the compression artifacts. So what we do is we narrow down and we say, okay, these are the objects of interest, all the ones that are in green here. We fetch them from disk and bring them into memory. So now we've got less of these compression artifacts now. We still have some compression artifacts, but we have less of them. And we do another try. We do another go at it. And we say, okay, now that we have a clearer picture on where the green salmon can be, maybe this is where the green salmon are. Right? And we still don't know because we still have compression artifacts. So these vectors might not actually be where we think they are, but we're getting closer. Right? So we have kind of we've narrowed down on the list of candidates that the user might actually be interested in. Right? And then you can kind of just iteratively keep on going. Right? You do another third try, and this time you read in the actual full vector from disk into memory. But notice how every time you do this reading, you're reading in less and less vectors, right? You started off with this kind of massive space of search opportunities, but iteratively you're narrowing down, right? Now this is the possible candidates that you have to search over. After the second try, you only have a very small number of candidates that you need to fully search over, right? So you're kind of setting out a big net, and then you're narrowing in on that on smaller, better candidates. And so at the end of the day, you get the exact same green salmon that you would have if you had not quantized, but you get all of the added benefits and the cost savings of having quantized. Right? And so the kind of the superhero here, the thing that's come to the rescue is that you have the full vectors on disk, not in memory, and you're doing disk reads and adaptive retrievals. The reason why it's called adaptive retrieval is because you have multiple retrievals that are kind of adapting to the vector quantization artifacts, and you're slowly removing the vector quantization, performing another retrieval, removing a little bit more compression, doing another retrieval, and you could this here I've just shown 3 rounds to get to it, but you can do this multiple times. And so by default, anytime you're enabling vector quantization in Weaviate, we only use adaptive retrieval to increase the recall. And it actually improves the recall a lot. So if I show you the true numbers, so that 95%, 83%, 65% was without adaptive retrieval. With adaptive retrieval, uh, if you enable adaptive retrieval, there's pretty much no loss in recall. It's a very minimal loss in recall. So let me show you some of the numbers here. So just a high level kind of recap of adaptive retrieval. You're doing multiple retrievals, and between each retrieval, you're removing compression artifacts so that at the end of the day, you get the exact right number of correct candidates. And so if you compare scalar quantization with adaptive retrieval to uncompressed vectors. So here on this graph, you've got queries per second. The higher, the better. So larger is better here because you can do more QPS, high throughput. And on the x-axis, you have recall. The higher, the better, right? So the ideal kind of situation here is that we want to be up and to the right. This is the uncompressed vector line, and this is the compressed vector line. And you can see how the compressed vector line for this 1 million object dbpedia data set, you always want to do compression because the compression is speeding up and it's all actually giving you better recall because we're doing the adaptive retrieval. So for this particular data set, now this is only for this data set. So if you're working on your own data set, you can run this benchmark yourself and see if it's different for you. But we ran this for multiple data sets and we saw the same pattern where it's a no-brainer. You just, if it's a 70% cost saving, a 90% cost saving, you automatically just want to turn on scalar quantization. So now it's not a question of kind of paying a price. It's just go with quantization, just compress the vectors. And so this is a default setting that we've now enabled to save customers money. And then if you look at binary quantization and product quantization, this is another graph where here you've got HNSW. So HNSW is not really important here, so you can kind of ignore this. But this is product quantization. So you can see how the QPS is a lot lower. And then this is your binary quantization QPS. And then this is your uncompressed index over here. You can see how the uncompressed is a little bit faster and has a little bit higher recall. But notice how these, if you think about the memory requirements here, this is the 32-bit floating point number per dimension. These are 1 bit per dimension, right? So if you look at the numbers here, this index, this green index is about 6.5 gigs of RAM. This orange line here is 700 megabytes of RAM, right? So there's a big difference between this. And the reason why it's not a 32x difference, like I mentioned before, is that it's not just the vectors that you have to store in memory. There's a whole kind of index that you have to store in memory. So there's a lot of overhead there as well. So the memory is not actually 132. There's a lot more that's going on behind the scenes, but the vectors are actually 132. That is true. Okay, awesome. So that's everything that I wanted to talk about, and hopefully I've convinced you that vector quantization paired with adaptive retrieval is really the way to go. Let me just take some of the last questions here. So there's one question that says, did you ever try a compression by singular value decomposition, SVD, for vector databases? Is it something that people would commonly do? If not, why? So SVD is typically not done. So something like principal components analysis, or where you're just keeping some of the dimensions. Typically, this is not done. I haven't seen people do this. It's interesting that you bring this up because just a couple of days ago, a researcher reached out to me and they're exploring this concept. I haven't read their paper or anything yet, but they reached out and I'm going to look into it. But from what I've seen, uh, none of the production level features that I've seen use that technique. And even so, they're building on top of SVD. So I don't know if they're using exactly SVD. But yeah, let me see if there's any other questions that I did miss here. Okay, I think I addressed most of those. Okay, I addressed the 1000 to 500 dimension. Feasible to implement dynamic compression. Yeah, so the dynamic compression is the main idea behind adaptive retrieval, so we address that. Yeah, so the different kinds of quantization is actually also possible. You can maintain a multi-index system where you can have one index that is 4-bit quantized, you can have another index that is 8-bit quantized, another one that's 16-bit quantized, and then you can perform kind of search to see which one gives you the best recall. That's also possible in Weaviate. I think that's everything, actually. Awesome. Thank you so much. If if you do have more questions, then feel free to reach out on my social media platforms. Um, you can also join our Slack community. And if you want to learn more, there's an entire Weaviate Academy. We've created courses on LinkedIn. We've created courses on Coursera, Deep Learning AI, Andrew Ng's platform. Um, we do a lot of education around the product because it is kind of an intersection of databases and machine learning. So there's a lot of people that kind of are wanting to learn one aspect or the other. So we do a lot of education initiatives, workshops, in-person events as well. If you have any applications or if you're building something cool, I'd be more than happy to help. I take one-on-one meetings all the time. If you want to go into any of these concepts and talk more in detail about them, I'd be more than happy to do that as well. Thank you all so much.
Thank you so much, everyone. Thank you, Zain.
Thank you. Take care. Bye.